All right, so this is going to be a rough draft video. I apologize for this being so late. I just got home and I did promise you I would get something out, so I definitely didn't want to let y'all down. So again, I'm sorry, but better late than never, right? So the quiz is going to be over SN2 reactions and probably a little bit of SN1 and also some of the E2 requirements. So let's just talk about SN2 processes. SN2 stands for a bimolecular, remember the 2 stands for bimolecular substitution reaction, right? Substitution reaction, right? And what that tells us is that the rate of this reaction is equal to the rate constant times the concentration of the nucleophile times the concentration of the electrophile. So it depends on both. So if you increase the concentration of the nucleophile by 2, so if you double it, then you increase the rate by 2. If you increase both the concentration of the nucleophile and the electrophile by 2, the entire rate increases by a factor of 2, right? Because 2 times 2 would be 4. So that's what that's telling us. But let's specifically look into the SN2 reaction. We know that SN2 reactions are a concerted process. So that means that as the nucleophile attacks and starts forming a bond with the electrophilic carbon atom, the leaving group leaves at the exact same time. So therefore, what we can think of when we have a strong nucleophile like hydroxide, and we have this is a primary alkyl halide, right? This nucleophile will attack, and some professors may prefer you to draw the lone pairs there. I learned that the hard way. And as you draw a bond to that carbon, you got to break a bond. Shout out Dr. Aguilar. So leaving group left, we have no more bromine on the alkyl chain, so Br minus. And we have that new bond that formed between the oxygen and that carbon. So we get ethanol, right? So that's our SN2 reaction, and that's just a very general SN2 reaction. What we see is when we have a strong nucleophile like hydroxide, we get an SN2 reaction, and this occurs when we have primary alkyl halides and methyl alkyl halides. Now, secondary alkyl halides can go SN2. However, as we see in this little chart over here, whenever you have a strong base and a strong nucleophile, just like hydroxide, because we mentioned at an earlier time that hydroxide not only is a strong nucleophile, but it's also a strong base, right? Remember, recall acid-base chemistry. We use hydroxide quite a bit. And we see that whenever we have something that's a strong base and a strong nucleophile, and we have a secondary alkyl halide, we get competing elimination E2 mechanism and SN2 reaction mechanism. And in fact, what you see, this tells us that whenever we have strong base, strong nucleophile like hydroxide on a secondary alkyl halide, recall secondary alkyl halides look like this. The major mechanism is the E2 mechanism, right? So let's talk really quickly about what the E2 mechanism is. This is a bimolecular elimination reaction. So essentially, whenever we have an alkyl halide, let's change it up. We've been using bromine quite a lot. Whenever we have an alkyl halide and we have an elimination reaction, what we're removing is HX. In this case, X is chlorine, and we're forming a double bond. And we know that you can form multiple products, right? So we realize that you can form multiple products here. However, we know one of these products is the major product because, one, it's the most substituted, and it also has the least steric hindrance, and that's going to be the first product here. major product. But essentially what the E2 reaction is, what is happening in an E2 reaction, and let me clarify that. We're not treating this with HCl like it was drawn. We are forming these products, and in the process we are losing HCl. And we're forming that double bond, right? So we usually treat this with a strong base, and most of the times you can use something like methoxide, but because methoxide is also a strong nucleophile, you get competing E2 SN2. So, but if we use something like, let's say, potassium tert butoxide, recall potassium tert butoxide is a strong base, weak nucleophile, right? Because potassium tert butoxide has this big alkyl group here, the tert butyl group, and it's just not effective at trying to get into these small places to perform this. So this does not work. Let's draw X. So that does not work. But instead, when you ever use something like tert butoxide, you're not going to get substitution, you actually get elimination. So what is elimination reaction? What are the requirements? So first requirement is obviously you need to have a good leaving group, right? Chlorine is a good leaving group because the conjugate acid, or the acid that it comes from, hydrochloric acid, has a pKa less than 0. So that means the conjugate base of it, chloride, is going to be very stable. Thus, it's a good leaving group. So that's one good thing. That's one requirement for an E2 mechanism. In addition, we also need a beta proton. So let's pretend this is how our compound looked in terms of stereochemistry. Well, we know that if this chlorine is going to the back and this one's coming out from the bottom and out of the page, then we know that those are on opposite sides. And in fact, if we want to draw, let's just draw a Newman projection, because it's always nice to see that down that bond. What we have here is a methyl here, a hydrogen here, a hydrogen here, and then we have a chlorine here, the methyl coming down, and that's the methyl I just drew, is that one right here. And then we have a hydrogen on that wedge with the chlorine. So this hydrogen on the wedge, the one that's underlined in yellow, is this hydrogen right here. The chlorine, clearly there's only one chlorine, that's that one. And what we see is that these, in relative to each other, they are anti-periplanar, right? That's the second, or that's the third requirement, because first requirement was we need a good leaving group. Second requirement was we need beta protons. We do have beta protons, right? These are our beta protons. So these beta protons are all red. There's 3 on this carbon, and there was another one on this carbon. So we got beta protons. That's second requirement. And then we need those beta protons to be anti-periplanar, right? So that's the requirements for E2 mechanism, or E2 reactions. And if you fulfill all these requirements, then you can eliminate this. And I don't believe you have to know the mechanism for this just yet, but we can do that real quick, just in case. So what happens is we have this base, right? We said tert butoxide is a good base, weak nucleophile, so it prefers elimination. Well, that base is going to take up a proton. So this is a proton transfer, right? And if you draw a bond to that hydrogen, you got to break a bond. And the bond that breaks here is the bond connected to hydrogen right here. And those electrons have to go somewhere. So they're going to be put onto that, into that bond to form a double bond. Because right now it's just a single, we form a double. What we see next is that if you draw this, essentially what we would get is a double bond here. But we already have 4 bonds to this carbon, right? So if we want to form a double bond here, we have to break one of those bonds, because if we don't break one of those bonds, then we have 5 bonds to carbon, and that's not going to happen. So what we see is, after you do this step again, these electrons go here. We have to break the bond, and the bond that we break is the one that's connected to the leaving group, right? Because we don't want to make carbon's not a good leaving group. We're not going to make carbon leave, because that reaction is just not going to happen. It's not a good leaving group. It would prefer the reactants over the products in that case. But because chloride is a stable base, and equilibrium favors the formation of the stable stuff, we form chloride over here, and we get these products. So let's see. Again, SN2 reactions. Now let's look at SN2 versus SN1 really quick, and this will be the last thing. SN1. So SN1 is a unimolecular substitution reaction. It is not a concerted process. This means it has two steps. The steps are, the first step is leaving, let's be like Dr. Reeves and let's abbreviate these. Leaving group leaves, and we form a what? That's right, a carbocation, right? And then second step is nucleophilic attack onto that carbocation. This one is concerted. So as leaving group leaves, nucleophile attacks. And I guess technically it should be the other way around, right? The nucleophile attacks first, and then the leaving group leaves once the nucleophile starts forming a bond. So that's the main difference between the SN2, SN1. But let's see. In order to think about which one's going to go SN1, we have to think about this first step here, carbocation formation. Every time you're given a methyl halide, so something like methyl bromide, or a primary alkyl halide, something like bromoethane, whenever you form a carbocation, if that leaving group leaves, as in an SN1 reaction, we end up with a carbocation on a methyl carbon, and then a primary carbocation. These carbocations are super unstable, so it's a big indicator to say, or to see a primary carbocation or a primary alkyl halide and a methyl alkyl halide like these, and to say, okay, that's definitely not going to go SN1, because if you made either of these into their carbocation, they're so unstable that transition state for that reaction is so high in energy, and the product is so high in energy, that this reaction is super endothermic. It's just not going to happen. So this is not going to happen. What we do see SN1 reactions happening with, SN1 with tertiaries, yeah, alkyl halides. So let's use iodine this time. And we see some of it with secondaries. Not as much though. So majority of them are going to be tertiaries though, just because those are the most stable. And what we see here is if you have a weak base but a strong nucleophile, examples of this include Cl-, Br-, I-, Cn-, SH-, or SME-. Those are very good nucleophiles but weak bases. So obviously a requirement for E2 mechanism is to have at least a moderately good base. But if you have a weak base and a strong nucleophile, it's going to go SN1 if you have that tertiary alkyl halide, right? And what we see over here is whenever you have a primary alkyl halide and a secondary alkyl halide, but you have a weak base, weak nucleophile, you don't get any reactions here, but you get competing SN1-E1 reactions. So again, if you can form a leaving group, you're most likely able to go, if you can form a carbocation, you're more likely able to go through an SN1 process, especially because, say we have a strong nucleophile here, or let's do one of those strong nucleophiles, weak bases. So let's choose cyanide. So this one here, it cannot just attack that because there's too much steric hindrance in the transition state. It's going to be too high in energy. That reaction is going to proceed very slow. Instead, what can happen is first, leaving group leaves, right? Step 1 of a SN1 reaction. Leaving group leaves. If you so you form iodide, and you have a carbocation on a tertiary. You have a tertiary carbocation. Now what we can see is this nucleophile can then come and attack that carbon atom, and we denote that with starting from the electrons. Remember, the arrows show the flow of electrons. So those electrons start at the lone pair and draw your bond to the carbocation. Do we have to break a bond when we do this? No, we do not, right? Because that carbon's already deficient in electrons, and we're trying to give it a full octet. Right now it has 6 electrons. We want to give it that full octet. So whenever that step happens, you get that product, which in reality is really just this, right? That's just another way of drawing it. All right. And, you know, later down the line, this is not applicable to you right now, but you can hydrolyze this, and I'm just a little bored right now. You can end the video, but this can happen. You treat it with some water and acid, and you'll get this guy right here. Boom, boom, boom. Yeah, you can end the video right now. I'm just having a little fun. And then water comes and attacks. So H2O, that carbon is now very electrophilic. And boom, 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 boom. O, H, boom, H plus, boom, boom, and H. What we can do is an intermolecular proton transfer. That'll go there, that'll go there. We can do boom, 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 boom. Still got a positive charge here. We'll do that. We'll do, those electrons will go onto that thing. And bam, 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 bam. Okay. I feel like I messed up somewhere. This is embarrassing. I'm hydrolyzing it. So many proton transfers got me messed up. All right, anyways, I'll finish this later.